Okay, so we have got day 2 here of PFT 101. So this is kind of the second half of the PowerPoint from yesterday, like, you know, at least in the way this PowerPoint kind of originally exists. This is the second half of chapter 2 in your regular NASM textbook, which is that sort of basic exercise science chapter. I like to think of it as the kinetic chain chapter because that's really what it is, although there is like one paragraph on the endocrine system that we'll cover today as well, where it's like, here's what hormones are. Cool, moving on. You know, NASM doesn't spend too much time on hormones, which is a bummer because hormones are a really big deal. But looking at the end of chapter 2 here, we're going to finish up. We talked about the skeletal system and the nervous system yesterday. Today we're looking at the muscular system. So we are going to review, for those of you who have already seen this, we're going to look more at actin and myosin proteins again, make sure that that's nice and clear, and then talk about like our connective tissues and things like that. So our purpose again is kind of understand the end of the kinetic chain here and its physiologic functions, how it adapts, how it responds to stress, and we are looking, like I said, at the muscular and the endocrine systems today. So your muscular system is, you know, if we kind of just give that like an overall big definition, right? It's a series of muscles that are under the control of your nervous system, and they're designed to generate internal tension, and that internal tension will allow them to move your skeletal system around. So that manipulates your skeletal system. So you've got these bones that are acting as levers, and you've got these muscles that are pulling on those levers in order to like change all your angles and, you know, manipulate your body in a bunch of different ways. And those muscles are shaped in a very specific way because the cells that make them up are shaped in a very specific way to have these special little proteins in them that allow them to shorten and relax. And that's something that you see that's, you know, unique in muscle cells, right? Like when we look at all of the different cells inside of our body, you know, they've all got their specialized structures. Like if you look at like osteons, which are, you know, the ones in your bones, you know, they're these really kind of long, thin, flat bones, right? I'm sorry, not long and thin, but like flat and like disc shaped, like frisbee shaped. And then like, you know, they're arranged in such a way that they kind of get, you know, one will lay this way and the next one will lay that way and then that will lay that way and then this one will lay that way. And that allows them to kind of have this really cool, you can kind of see like this interesting little structure here, right? This little twisty structure. That's what allows them to be very like hard and compact and allows your bones to be very, you know, like stiff. And that's what allows them again to act as lever. That gives us a nice strong framework, right? And then you look at like neurons and you look at their special structure. Neurons have got all their little fingers, right? And those little fingers reach out and grab to like, you know, attach themselves to other neurons. And then, you know, those fingers attach to other neurons, which attach to other neurons. And so they're really good at, you know, creating a network. And then they're also really good at transmitting electrochemical signals, you know? They've got all these, you know, you don't see it in this picture here, but like if you zoom in and you look at like the axon of a neuron and you look at, actually, that's not quite zoomed in enough. Sodium, potassium. You look at like the axon of a neuron, you'll actually see it straddled, like its membrane is straddled like this, where it's got a sodium pump and a potassium pump and a sodium pump and a potassium pump. And it just kind of goes back and forth so that it can push sodium and potassium back and forth, creating electric charge. That's how your neurons generate electricity, using those action potentials, you know? You can kind of see that happening here. Like there's sodium and there's potassium. There's a little chlorine as well in there. And so like, you know, that shifting back and forth, I always like to think of it like honestly, the easiest way to understand it, because it's a difference in charge, right? You got negative and you got positive. That's generating electricity in the same way that taking two socks and rubbing them together, and all of a sudden you get static electricity. You know, that's exactly kind of what's occurring there. Can I tell you guys, you know, it's just really quickly, we were talking earlier a little bit about how like, you know, I played a bunch of spike ball yesterday and I was like I was like getting nauseous because I did it like right after I went for this big trail run. And I was like exhausted and hungry and I just like didn't get to eat for like 4 or 5 hours. And I was just like, oh, I'm going to kill someone. But I go to like make a protein shake and I pull out my, my shaker, right? Like a shaker like this. And I get the lid off and I'm sitting there and the sun's hitting it and I'm looking and there was so much static electricity on the plastic of like the protein shaker that I had made from like all this friction from like, you know, I had like a towel there and stuff. And there was all this like static. And as I was like pouring the protein and you could see little bits of protein powder, they would like go into the shaker. And then before they would land, they would come back out and just be projected in like a mushroom cloud away. And the static electricity was keeping my powder from like the any of the really loose like tiny particles from actually landing in the shaker. And I was like, that is so freaking cool. Anyway, I nerded out on that yesterday and I was like, I'm gonna tell my class about that in the morning. But that's, you know, when you look at a neuron, right, you've got these sodium potassium pumps and that's what's generating electric charge. They have this special shape there. Well, if you look at muscle fibers, they've got the same thing. You look at like a muscle fiber, which is what we call a muscle cell. They're also straddled with sodium and potassium pumps around the outside. And that's what allows them to generate electric charge as well. But on the inside of your muscle cell, you're going to see all these little special proteins down here. This is your actin and myosin strands. You got actin, which is the thin strand, and then you got all these like little myosin heads here in the middle. And so like, you know, these special shapes are what allow your muscles and your neurons and your bone cells and everything. These special shapes allow them to have that special function. So again, you know, form follows function follows form, you know, like all of it is related. If you want something to perform a certain way, it has to look a certain way. And so that's sort of a big part of what we're going to talk about today, because that's especially important when we talk about muscles. You know, like muscles have so many special shapes and that are relevant to like what we do. That's what allows us to kind of, you know, move around and do everything. And so when we look at the structure of our skeletal muscle, right, it's a compilation of a lot of individual muscle fibers that are wrapped together in connective tissue. So we're going to start this talk by looking at like the large. We're going to start by looking at like an overall muscle itself. Then we're going to zoom in and eventually get to muscle cells individually. So the first layer is like, and we're going to go from the outside in, which is very weird actually. I don't know why they do that this way. I kind of like going from the inside out, but whatever. So the first bundle is the actual muscle itself, right? Like that's the you know, like if you were just to like peel back my skin and pull out my bicep, right? Like you would have just the muscle itself. And so that's wrapped by an outer layer of connective tissue that we call fascia, okay? So your fascia is this stuff right here. When you look at fascia, it is this kind of web-like connective tissue. Oh, that's a really great one. There's all the fascia in your hand, for instance. That's kind of cool. One of them that usually gives people a little bit of, here's some, your thoracolumbar fascia down here. There's a little bit of fascia on the inside of your chest here. And then one of the most common one that we end up talking a lot about is the fascia on like your IT band, right? Like your IT band is very, very fascial. This is a kind of a weird picture to find it, but like there, right there, this like big band on the outside there, right? Like that's your IT band. Yeah, it's muscular, but it is kind of like this big, it's got so much connective tissue in it. This is why we often hear about people getting like a rubbing sensation on the outside of their knee or a rubbing sensation at their hip, where they'll get like runner's hip or runner's knee. And what that is, that's that fascia tightening up. And this connective tissue is designed to make sure that like, you know, our muscles stay going in the grain that they're supposed to, and it, you know, creates stability, right? It's kind of like a saran wrap around your body to make sure that everything is held where it's supposed to be held. But the problem is fascia, because of how tightly wrapped it is, it gets so tight that sometimes it causes like our muscles to rub because it gets, our muscles are maybe like a little overactive or something, right? Here's, by the way, here's your fascial lines, which is kind of cool. You can see they actually kind of wrap around the body. You know, again, this is kind of like if you were to, how did somebody put it one time? It was like if you were to ship like a human body across the, you know, across somewhere, and you need to like wrap it to make sure that it like didn't fall apart in transport. It's like this, these are the main places you'd be like, all right, I need to create some stability here. I want to make sure that that arm doesn't pop off, you know. And so it's, you can see this kind of wrapping around the body there. So that is, those are very much like our fascial lines. So that's the outermost layer that surrounds all of our muscle. It's not necessarily the muscle itself. It's kind of around the outside of the muscle. It's almost like its own tissue in a way. It's connective tissue. The inner layer around that fascia, which is the outermost layer of like the wall of the overall like muscle itself, right? Like the surrounding outermost tissue, that's going to be your epimysium, right? And it's epi because it's around the epicenter, right? It's around the outside. So that's your epimysium around the outside part of the muscle there. Then, so like if you were to like go by like, and by the way, you've seen fascia, like if you go by like a steak and it's got that silver skin, right, and you take that off, that's the fascia, right? And then that outermost layer right after that would be the epimysium, right? Then you go one layer down, and that's where you're going to start seeing like fascicles. So when you look at like layers of muscle fibers, right? We talk about that epimysium, right? That's that surrounding layer right here. But if you go one layer in, now you've got like a bundle, right? So you've got this like bundle here, and you got a bundle there, and a bundle there, and a bundle there. And then each of these individual bundles, guess what? They're made up of bundles, right? So there's a whole bunch of like individual little fibers in there. I'm actually going to use this one. So you see like, here's a single like myofibril. This is an overall like muscle cell. That muscle cell is coming together with all these muscle cells, and then it's all wrapped together in what we call a fascicle, right? So a fascicle is what is a bundle of individual muscle cells. And then what a muscle is it's a whole bunch of fascicles all wrapped together, and there's that epimysium around the outside, you know, holding all of them together. So that's your next layer, right? So you got the fascia on the outside, you've got the epimysium just in of that, then you've got the fascicle in there, and the fascicle has to have a wrapper around it to hold it together, right? And so that is going to be called your perimysium. That's around the perimeter of a fascicle, right? Then each fascicle, like I said, is made up of individual muscle cells. So each individual muscle cell is held together with one outermost layer. I showed you that earlier, right? I showed you where the muscle cell had its sodium and potassium pumps, kind of like a neuron. Well, that was the outer layer. That is called the endomysium, endo for being inner, right? So there's like a bundle of a bundle of a bundle, all that comes together, and then it's wrapped in an outer layer of fascia. And that's sort of what our muscles actually kind of look like. And what's nice about that, what's the reason we have this arrangement, right, is when your nervous system is going to recruit, like this is an individual muscle cell, right? And it's got all kinds of little tiny myofibrils in it, and those myofibrils are what actually make the contractions. Well, see this right here, like this fascicle has, let's see, we're going to count them out. I know it's weird. 1, 2, 3, 4, 5, 6, 7. We're going to assume 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 25, 26, whatever. There's about 25 individual fascicles in, I'm sorry, 25 individual muscle cells in this fascicle. Now, if I have, you know, I want to make, and we'll just go ahead and forget about these other fascicles here, right? There's 25 muscle cells in this fascicle. So if I wanted to make a contraction for 20% of my 1 rep max, right? I can lift 100 pounds and I need to lift a 20-pound dumbbell from the floor and I need to put it on the rack, right? That's 20% of my 1 rep max. My nervous system is going to recruit 5 of these. It's going to recruit this one, that one, that one, that one, and that one. There we go. There's 5. It doesn't need any of those other muscle fibers. And that is why we have this arrangement. That's how we are able to create strong contractions versus weak contractions. What determines like how strong a contraction is how many individual muscle cells, muscle fibers, get recruited during a muscular contraction. And it's kind of like a floodgate situation. Like what'll happen, like when you go, you kind of want to think, you can't think of it as like a floodgate. And what I mean by that, let me see if I like floodgates. Not like real diagram. I don't know how to picture it, draw it any other way. All right, I'm gonna have to make my own. Okay, so it kind of looks like this, right? Imagine like there was like some flooding that happened, right? And so you've got to have like these different compartments. So you had like one here, and you have another one here, and another one here, and another one here, right? So like when this starts, you know, when this overflows, you know, it's eventually going to go to here, and then it'll eventually go to here, and then it'll eventually go to here, right? that's actually kind of how your muscular system is arranged in how your nervous system recruits muscles, right? So, it might start with this one here, and don't worry about the size of these, just worry about them as like 1, 2, 3, and 4. Let's say you go to lift like a super heavy barbell off the ground. Your body's going to try to recruit as few motor neurons as possible at first. So it's going to try to get the job done with just this many motor neurons. Maybe that's not enough. So then it recruits this one. Still not enough. It recruits this one until eventually, if you're lifting at like 100% of your 1 rep max, you will recruit all of the muscle fibers, right? You will do every single one of them, if that diagram kind of helps. This is kind of how I picture motor unit recruitment in my head. I think of it as like these little floodgates almost. So that's why we have this arrangement here. That's why we have like this muscle cell, right, is going to get recruited, but maybe this one over here doesn't, because it's not that strong of a contraction. Because here's the thing, when a muscle cell fires, and we're going to talk about this in a little bit, we have this principle, we call it the all or nothing principle. And when a muscle fiber fires, it has to fire for 100% of its maximum effort. Muscle fibers fire completely or not at all, right? So then if that's the case, then how are we able to regulate our strength of contractions? We just recruit less muscle fibers, right? We recruit this guy here, but we leave this one turned off. And that's how, you can go pick up a super heavy barbell, but then you go to pick up a puppy and you don't go, like, oh no. Like I heard somebody like talk about like one time they were, this is so dumb. I apologize for even bringing this up. Somebody was talking to me about like comic books. And they were like, it's so dumb that Superman is as strong as he is. He would totally just like rip through the whole world like tissue paper every time he tries to do anything. And I was like, actually, he only has to recruit certain neurons the same way that you can actually pick up something very, very light and something inside. It would just be a larger scale, but it would still be the exact same thing. He's just working at a much lower percentage of his 1 rep max all the time compared to us. There's a very nerdy, real conversation I had once. That's like a PSA for you guys, like don't do this. It makes you the worst. So that layering, does that all make sense to you guys? Do you understand like how that kind of layering all comes together? Let me see look for thumbs up. So really quickly, just kind of reviewing the terminology we just went over. Like, so you've got muscle bundling, right? Oh yeah. What's up, Erin? Question.
So the fascia, Brad, that's on the very outer side of the muscle.
Yeah, and it's connective tissue. It's not necessarily a muscle itself.
Connective tissue. Okay.
Yep.
And then within this, you know how there's the muscle cells that you just showed us? What's on the outer side? What's on the outer part of the muscle cell?
What do you, you mean like, what is this outer like layer here? Like this little like wall?
Yeah, what's the most outer layer of a muscle cell?
So the little outer layer of a muscle cell itself, right? That is the endomysium. So if you look at the endomysium of a muscle cell, you will see a lot of the normal materials that you would see around like your average other cells, right? You would see, like I said earlier, you would see these sodium potassium pumps. There we go. This will kind of work. So there's the endomysium, right? Which is really just like an outer layer that's just there to kind of wrap everything and hold it together, right? But you see this like little purple thing here, right? That's actually a nucleus for a muscle cell. So this is a muscle cell, and the muscle cell's got a whole bunch of these special little proteins in it. See these little dark bits in here? That's specialized materials that are running through your muscle cell. So let's look at a muscle fiber anatomy biology. So let's take a look at an individual muscle fiber. So a lot of, see, this is the problem. They're only spending time they're really, really, really focused on just showing you the sodium or the myofibrils and stuff, which is great because we do spend a lot of time talking about that. But I do kind of want to see a lot of those other materials. You're going to see on the inside of the cell, Irene, the same stuff you would see in any normal animal cell, right? Let's just pull up this one. This will be fine. I'm sure I can find it. Oh, this is actually super zoomed in. Okay, this is great. All right, so here's an individual, like again, right? Here is an individual muscle fiber. And inside this fiber, see all these myofibrils, right? This is one cell we're looking at in this picture. And then here's the outermost layer. And along this outermost layer, you can't really see it here, but you're gonna find sodium and potassium channels, right? So sodium, potassium channels, pumps, cell. So if you look at like the outside cell wall, right? Your cell wall is this phospholipid bilayer, right? It's that layer of fat that actually surrounds all of our cells, right? Every cell you've got is surrounded by this like fatty layer. And it looks like this. It looks like where you can see like the fat side is on the outside and then the protein side is on the inside, right? And so like that creates like the protein side's on the outside, the fat part is on the inside, and that keeps water in and keeps water out, right? And then see these little channels right here. That's what allows materials to pass through this impenetrable wall, the endomysium, right? These little channels here. Now, the things they mostly want to pump are things like sodium and potassium, and that's how each individual muscle cell can generate electricity. And generating that action potential, that electricity, right? What that does is when we get into this later, that allows it to, when that electric signal rushes across this whole muscle cell here, what it will do is it will release calcium into this network of tubing here. And that calcium is what allows, actin and myosin to finally bind together because, the protein that's blocking them from binding kind of gets out of the way. And then see this right here, there's some mitochondria in there. So what is made up of that outermost cell wall? The same thing that's made up of any outermost cell wall, except that this one's got a lot of extra sodium and potassium pumps so that it can generate electric charge. Does that answer your question?
100%.
Did it? Okay, good. I was like, I wonder. I was like, man, I'm getting a little ahead of myself here. So that's good. So
love the explanation. Thank you.
Yeah, well, thanks. So yeah, you've got energy producers running throughout the whole cell. I was worried. See, the problem with like the way they always show these pictures is like they only ever show you the stuff that's like important to muscles themselves. Like there's also lysosomes and cytosol. There's all this other stuff in here as well, but they're not really showing all that. That's why when we teach biology, we usually spend all our time teaching you like, an animal cell. We just teach you like your classic like animal, blob cell. And there's no cell in your body that actually looks like this, like the closest one is like a fat cell because it looks like this and then there's an extra sac around the outside. So it's somewhat close. But there's all the normal little stuff you're going to find in a cell. Well, there's special stuff in muscle cells. So reviewing what I just talked about, right? Reviewing sort of the overall big anatomy, right? You've got a muscle, and a muscle is made up of a bundle of fascicles. What is a fascicle? A fascicle is a bundle of muscle fibers, which is what we call a muscle cell. What is a muscle fiber? It's a muscle cell. I walked myself into a corner with that sentence. It's a series of actin and myosin proteins overlapping each other, right? And then all of your muscles will eventually end in more connective tissue. And the end of your muscles, that other connective tissue, is going to be what we call tendons, right? And tendons are what are going to attach your muscle to a bone. And you can see here, I always talk about how much I kind of hate this picture because they're showing you ligaments and tendons kind of simultaneously. So here's this is attaching this femur to the fibula here, right? So that is a ligament that's attaching a bone to a bone. Well, you see this little white section here that looks really similar. That's a tendon, right? And this is your quadriceps tendon, which runs to your kneecap and over top to insert onto your tibia here. And that way, when this muscle pulls, it's pulling this bone in this direction and it causes knee extension. Just like, and you're not really seeing the other back side of it here, your hamstrings run, from the same part, but on the back of this bone here, and they insert onto the back of your tibia and they pull your knee into knee flexion. So you've got antagonist muscles on either side of the femur there, both inserting onto either side of the tibia. One does knee extension, one does knee flexion. Now, tendons and ligaments are very, one of the reasons they're so confusing and people get them mixed up all the time, they share a really common trait, which is that they have very, very poor blood flow. They both just do not get as much blood. There just aren't as many blood vessels running to these types of tissues as other parts of the body. Like your muscles are so hungry to produce energy, they need oxygen delivery all the time. They're producing ATP constantly because that's what allows them to do that, contract, relax, contract, relax. So they're just producing ATP a lot, and that, burns a lot of energy. And so muscles are really, really hungry. So your body's arranged in such a way, it's like, well, we know that's going to be hungry. We're going to make sure that it's easy to deliver food there, and so it's going to have lots of blood vessels running through it. But your tendons, they don't get quite as much blood flow because they tend to be just a really stiff thing to insert onto a bone. We actually don't want them to be too malleable, because then they wouldn't be able to pull on the bone hard enough and they wouldn't be able to get a good enough grip. So we actually don't have as much blood flow there because of how stiff tendons are. Well, that's great because it allows them to, be super springy and produce force and have a good grip. But it's not super great for the fact that they repair very slowly as a byproduct, right? They're just not getting as much, nutrient delivery, so they tend to repair very slowly. So that poor blood flow is actually something we need to talk about. We need to find ways to promote blood flow to that connective tissue if we want these types of tissues to repair. Well, lucky for you, we can always lift for a relatively light amount of weight. That way we're not, exerting maximal effort on that connective tissue. And we can, lift at a very slow tempo. By being under tension for a very long time, that's actually going to promote greater blood flow to the entire area. And by doing little tiny micro movements where you're kind of wobbling a little bit, you're actually pulling and kind of sending little bits of blood flow to that connective tissue. And that's why stabilization is all about strengthening your connective tissue. And it's about two things. It's about strengthening your connective tissue and allowing connective tissue to repair. And it's about teaching your body how to do things. And you get both of those from going slowly and lifting in an unstable environment. And if we know that as a physiologic fact, if you were to create an OPT model, right, and you were to create your own style of working out, you'd probably follow the same protocol as NASM does. You would do a slow tempo, maybe 4-2-1, and you would lift in a very wobbly, unstable environment. And that's why the OPT model is the way it is. Any questions so far? You guys feeling good?
No, I'm good.
Awesome. All right, let's take a look at the muscle cells. I kind of got a little carried away because I'm caffeinated and high energy right now, and so I stayed up too late. So now we're looking at our individual muscle fibers, right? We're looking at our individual muscle cells. So we've got our cellular plasma, right? Inside of a muscle cell, we've got our cellular plasma, right? This is going to be your sarcoplasm. That's just a special name for that fluid portion, right? We're going to have fluid in all of our cells. We're going to have we usually call it cytoplasm, but in individual muscle cells, we call it sarcoplasm, because sarco is Latin, I think, for flesh. So cellular plasma, we refer to that as sarcoplasm. And then it's going to have all the normal stuff you're going to see. It's going to have glycogen in it, so that, if that cell needs to produce energy, it can have it. Fats, again, for energy production. Minerals to help with action potentials and things like that. And then it's going to also have myoglobin in it. And myoglobin is that special protein that attaches to oxygen and allows, oxygen to kind of be carried throughout the muscle. And we need oxygen to be able to, again, produce ATP. So that's this kind of special materials you're going to see a mitochondria, right? That's sort of another one of our regular players that we find inside of most of our cells, right? The energy producers, right? Then we see a nucleus in there, right? That's the command center of your muscle. It's got all kinds of DNA that's designed to teach your muscle cells how to grow and how to function and stuff. But the one thing that's unique inside of an individual muscle cell is that it has got myofibers myofibrils. And myofibrils are these specialized structures that contain what are called myofilaments. And we'll look at the three types of myofilaments here in just a second. That's what allows your muscles to actually contract. So when you look at a myofibril, right? A myofibril is this whole section right here where it's all like a series of like little proteins kind of all held together, right? So myofibril is not the most important term in the world, but it's like a series of like, this is a sarcomere here, there's another sarcomere here, right? And what a sarcomere is it's this area where these myofilaments, which are really important, are overlapping each other. So you've got two myofilaments. You've got actin myofilaments and you've got myosin myofilaments, right? Those are the two main ones. Then you've also got, these regulatory proteins we'll look at. And so, this area where, actin and myosin are crossing over each other, that's called the sarcomere. It's the area where that's happening. And so you've got a sarcomere here and here and here and here, all of them laid end to end to end to end. That is the myofibril, right? So a myofibril is basically this big long strand containing a bunch of myofilaments. So we're really, really zoomed in here, like we're zooming in like crazy. So looking at those contractile elements, right? If we're looking at it, right, we've got our sorry, that's my boss calling actually. Give me one second, let me just text her. You know what? Let me answer this actually. 1 second, guys. This is we're gonna take a 5-minute bathroom break. But I'm gonna keep the recording going. So if you're on YouTube, skip forward to when I come back and start talking again. 1 second. Let me just take this. Hey, what's up? Sorry, I'm in class. What's going on? Yeah, I sent her an email. I couldn't find her phone number. Okay. I lied. It wasn't 5 minutes. Do I have everybody? Is everybody here? Raul, Ariana, Robert?
Yeah, I'm here.
I'm here.
2.
Here.
Hey. All right. We're back. Okay. Now I really do feel like a teacher on Zoom. There's nothing. Have you guys seen all, like, there's so many memes about like, is everybody here? Okay. So, where were we? We were talking about myofilaments, right? So a myofilament, these are all the individual little proteins that you're going to see. So myofibrils contain myofilaments, which myofilaments are the contractile proteins within a muscle, right? So there's two main categories. You've got actin, which is this thin little strand here, and myosin, which is this thick strand in the middle, right? And so when you look at like a muscle, and you look at like actin and myosin contractions, I want to find a picture here. 3 different lengths, please. Maybe. Oh, this will work. Okay, so you can see here, this is how they're kind of arranged, right? You can see like they're overlapping each other. And so the thick filament here in the middle, it has all these specialized little heads. I'll kind of go back to the PowerPoint for just a second. So you can see all these little club-like heads on here. And those club-like heads, what they do is they are able to reach up and grab that little myosin strand. And when you look at a myosin strand, you will see, you can kind of see all of these individual, oh, that's super tough. Okay. Guys, this is actually, okay, I apologize. The reason we're having a little bit of a weird morning, we've got a new student who's trying to join us. I tried to get a hold of her yesterday and I wasn't able to. And so now she's very panicked and they're asking me to throw her on the call now. Man, she is about to be hit hard with some heavy biology.
Yeah.
I kind of feel bad for this poor girl. Yeah, let me give her a call really quick. We're gonna try and get her on this call, and we'll all welcome her with open arms because we're happy to have a new student. Yeah, I'm sorry, this is the weirdest Zoom call, but I will say at least it's some variety, right? At least like weird stuff's happening. Maybe that's just me and my no sleep crackhead state. Hi. Hi, this is Brad over at Sochi. How's it going? So we're I wanted to give you a call because we're trying to get you onto our Zoom call. Oh, okay, shoot. Okay, so you have Zoom already pulled up? Okay, I'll tell you what, why don't I can shoot you a text right now. I'm a little worried that I might have sent you an email. I think I'm a little worried that I have the wrong email. Like I might have like a number out of line or something. Let me, can I text you? Hold on, give me 1 second here. Sorry, I'm just having a little sketch. Okay, so I sent you the meeting ID. All you got to do is punch in those digits, and it will it'll add you into our call. We'll see how that's working. And how do you pronounce your name?
Eugenia.
Eugenia?
You can name you Jane.
No, what do you prefer? What's your, I don't like doing that. Eugenia, is that the one that you like?
Eugenia is good, yeah.
All right, that's what it'll be then. Let's see here. I don't quite see you just yet. Oh, awesome. Look at that. Boom. All right, welcome, welcome.
Are you Brad?
I am Brad. I'm gonna go ahead and I'm gonna hang up on the phone here real quick. All right, well, welcome to class. So we're in the middle of talking about how muscles actually contract. I gotta warn you, we were talking a little bit about this before. As I was kind of getting you into this call, I was like, man, this poor girl is about to get hit really hard with some technical terminology. But don't sweat it. I'm going to get you caught up probably after. We're going to move through this a little bit, and then you and I can stay on the line, and I can get you caught up afterwards. Does that sound good?
Yeah, thank you.
Awesome. All right, so what we're talking about right now is we are looking at how in an individual muscle cell, right? So when you zoom all the way into a muscle cell, what you will see are these really cool special little proteins. And those special little proteins, they look like this. They're arranged like this. They're called actin and myosin. Actin is this little thin strand right here, and myosin is this really thick strand in the middle. And they're shaped really cool. They got these really interesting little shapes on them. If you actually look here, you can see all these little individual little bulbous kind of head things, right? These little heads, they like to reach up and they like to grab these little binding sites that are going to be found on these little thin strands. And then what will happen is once they reach up and bind, they'll actually pull. And so these little heads, like they'll kind of pass this little strand here from head to head to head to head. And so, you know, this guy will reach up here and it'll pull it. And then this little band will kind of move over to the left here. And then in the next head, will grab it, and the next head, and it kind of pulls it almost like hand over fist, almost like you're pulling a rope. And what will happen is this little blue line here and this little blue line here, you know, this one's going to get pulled this way towards the center, and this one's going to get pulled this way towards the center. And that's what happens. And you can actually see that happening kind of in the second picture down here. See how they're barely overlapping, but now they're very much overlapping. And so this is a relaxed muscle cell up top, and this is a contracted muscle cell down below. And so that's what's happening in an actin and myosin contraction if we look at it, right? And you can kind of see that happening right here. We'll see, you know, where it's like they're reaching up, and so the whole thing kind of pulls together like that. It gets thinner and you know, closer and closer and closer together, and then eventually, well, because this is an animated GIF, it's just snapping back into place. But what it'll do is it'll actually relax sort of slowly back to length. And if we zoom in a lot, by the way, here's what it really looks like. Kind of crazy, right? And it looks like a little creature walking. But that is actually what's happening in your individual muscle cells. Now, what's cool is that is happening in every single muscle cell simultaneously whenever you create like a muscular contraction. So we're looking at these little proteins here. You've got actin, which is the thin strand, right? So actin is this strand right here. These little red strands are getting pulled inward, right? That's actin. And then myosin is this thick strand in the middle with all these little heads on it that's actually doing the pulling, right? And so you've got actin and myosin. Those are the two special proteins found in every muscle cell that you've got. And there's thousands upon millions of them throughout your body. So those little binding sites, you know, what happens is that head reaches up. Now, here's the thing. They always want to bind together. Like these two proteins are really, really, really attracted to each other. And so they constantly want to bind together. But we don't want that to happen. Like when we want our muscles to be like relaxed, right? We don't want them like bound together. And so what we have instead is we have these regulatory proteins that actually sit on the thin strand. They sit on the actin, and they're there to make sure that myosin, that little thick filament, can't reach up and bind. They're there to block it. Whenever we want our muscle cells to relax, that's where we have these little like special proteins that block their little like grabbing sites, right? So if we look at like troponin, tropomyosin, can I get a GIF here? Is that what we're gonna animate? Yeah, totally. So you can see like what'll happen. See this little like these little like red dots here that are kind of covered by this little strand? That gets moved out of the way, and that's what allows that binding to take place. So, you know, they can't bind together until this actually binds to it, right? And once it moves that out of the way, then suddenly the actual contraction can occur, right? So this is gonna, actually, here's a really great picture. So these are little calcium ions. That's gonna grab it and pull that band out of the way, right? And now those sites are exposed. So these little heads here are like, oh, sweet binding sites. And so they're gonna reach up and grab, and they're gonna pull, and then that's gonna shorten it, right? And then that whole sliding action kind of occurs, and your muscle cell goes from being this long to being this long. And that's how your muscles go from being this long to being kind of bunched up like this, right? Like they get bunched up, you know, and bound together. And that's what we're sort of looking at there. And that is sort of a muscular contraction in a nutshell, right? So actin's the thin filament, myosin is the thick filament, and then troponin and tropomyosin, they are the binding blockers. They're there to make sure that a muscle can relax when we don't want contractions to take place. Now, the whole area where this is happening, this little section here, from this little blue line to this little blue line, we're going to refer to that as the sarcomere. That's the area between what we call two Z lines. The sarcomere, and this is a key term that you'll often hear in your textbook, it is the functional unit of your muscular system. And what that means is like your muscular system's able to act the way it acts because of all of these individual little sarcomeres. So you have to have these sarcomeres here in order for that to happen. How are we doing so far, guys? Feeling good?
All good.
How we feeling? I'm gonna mess it up. It's Eugenia?
Eugenia, yeah.
Eugene, is it Eugenia or Eugenia?
Eugenia.
Yeah, okay, cool. I'm gonna get it. My name is Brad, and a lot of times that name is usually Bradley. Like that's usually like the long version of Brad. But my name is just Brad, and my middle name is Lee. And whenever I was in trouble as a kid, my mom would call me by all three names. She'd be like, Brad, Lee, Thompson. I'd be like, you know. So whenever people call me Bradley, it drives me a little crazy. So I like to call people by like what they want to go by. If you've got a nickname or anything, I want to call you that. Okay, so now that's those special little proteins there. That's your troponin and tropomyosin, right? Those are the ones that are stopping those protein contractions from taking place, like we mentioned. Now that we kind of understand all of that, right? If we look at like all those individual like myofilaments, and we understand, you know, the little proteins that are inside, we need to understand how our nervous system kicks this all off, because your muscles will actually do that. This will be a kind of a weird thing to show you. But like you can create muscular contractions without your nervous system technically. If you do dropping acetylcholine on a muscle. This will be a little bit of a weird video. If I can find it. Actually, I don't think I can. Yeah, I'm not gonna quite find it. That's probably good anyways. Because it's gross. But if you were to like, let's say you had, let's say you pull out like an individual muscle fiber, right? And it's fairly fresh. If you were to drop like an electrochemical on it, right? It would actually make that muscle fiber contract. You can get a heart to start beating again. You can get muscles to contract, you know, and that's because your muscles are controlled by your nervous system, which uses chemicals like electrochemicals in order to create these muscular contractions. So we need to understand how our nervous system is connected to our muscular system. We need to understand how those two things sort of function together in order to create these muscular contractions that we're talking about. And we call that neural activation, right? It's where your nervous system generates a contraction in a muscle, right? So neural activation is essential in order for you to be able to manipulate your body. And so there's a constant communication network happening between your nervous system and your muscular system. And you can kind of see that right here, right? Here's like, this is like one of your individual like spinal discs. You've got your spinal cord kind of running through this here. And then there's these little roots here, these nerves that kind of run out from there. And so what'll happen is like information will come in, you know, let's say that information's coming from like this little like receptor called a muscle spindle that lives inside of your muscle, right? And so that muscle spindle saying like what length a muscle is or how much, you know, how much force is being generated. So that information is going to go, you know, to your nervous system and then travel up to your brain, and your brain's going to go, okay, well, I'm trying to generate, you know, lots of force in that muscle. So then what it'll do is it wants to generate force. So then that signal will travel from the brain back down the spinal cord, and then some of it will travel to the muscle that you're trying to contract, and then another signal will travel to the muscle that you're trying to relax. And that way you're not going to pull on both sides of your bone, which would result in your arm like not moving. So, you know, if I want this muscle to contract, I need this opposite muscle to relax. And so when, you know, I am getting information from here that goes to my brain's going to go, okay, great, squeeze this, relax this. And so then all of a sudden that's going to create that elbow motion that we're talking about, right? So we've got an information going towards the brain, and we've got two pieces of information coming from the brain. One is relaxation and one is contraction. So that generation of force, that nervous system creating that action, that all happens thanks to what we call a motor unit. And a motor unit, this is one of our most important kind of key terms here in this chapter. A motor unit is a single motor neuron. So it's a neuron from your nervous system and all of the individual little muscle fibers that it's attached to. So what's kind of cool is like if you look at a motor unit is actually, you know, one neuron. You can kind of see the tail end of the neuron here. But then like see how it's attached to like this muscle fiber and that muscle fiber and that one and that one and that one and that one and that one. It's attached to a lot of individual muscle. So one neuron zaps, you know, 20 to 1,000 motor neuron or muscle fibers, individual muscle cells. And so that's what's kind of cool there, right? You've got one neuron zapping multiple cells. And by zapping those multiple cells, you're able to contract several muscle fibers simultaneously. If you recruit like 2 motor neurons, well, now you're recruiting lots of muscle fibers, right? So that's how we create like weak contractions versus powerful contractions. If I've got one neuron that's recruiting like maybe 20 muscle fibers, that's going to be a really weak contraction. You know, that's maybe something that like moves my eye around, right? Really tiny itty bitty weak contraction there. You know, I've got maybe 20 muscle cells, you know, moving my eye back and forth. But let's say I'm doing like a really heavy barbell squat, right? I might be recruiting, you know, 1,000, you know, 5,000 muscle fibers all simultaneously to kind of lift this super heavy barbell, you know, back up to a standing position. You know, like if I've got a barbell on my back, I've got all these individual like motor neurons that are recruiting thousands and thousands of muscle cells inside this really large muscle here. And so I go down and then I'm recruiting a lot to kind of get myself back up, right? So that arrangement is what allows us, again, to have weak contractions versus strong contractions. I'm going to make up a number here. Let's just say I've got 500 neurons firing when I lift like a 200-pound barbell. Well, if I lift a 100-pound barbell, maybe I only need 100 of those neurons, right? So my nervous system can now control how strong I make a contraction. And so when that happens, when you have like neural activation, that's going to trigger that sliding action that we just talked about. My neuron is going to zap a muscle cell, and then that muscle cell is going to trigger the actin and the myosin proteins to slide across each other like we talked about. And that's what we call neural activation. And it does all of this thanks to these chemicals. It does all of this thanks to chemicals. And I'm just going to kind of go through this pretty quickly here. But what happens is like kind of summarizing everything. is an electric impulse will travel from the nervous system down the axon of your neuron. Eventually, that neuron will, sort of attach to a muscle fiber, and it will zap that muscle fiber. And when it zaps that muscle fiber, the muscle fiber uses this chemical to communicate between the nervous system and the muscular system. And that chemical is called acetylcholine. That's the chemical I was talking about. If you were to drop that on a muscle cell, it would contract. And so then that acetylcholine binds, which causes electricity to run throughout the muscle. That electricity causes the sliding action to occur inside of our muscles. It causes the actin to bind to the myosin. So that whole process, by the way, is called the sliding filament theory. A lot of times we call it the sliding filament model. And what we're saying is like a sarcomere, the area between two Z lines where the actin and the myosin are crossing each other. The sarcomere is going to shorten. It's going to shorten from one area, over here and over here. It's going to come closer together, and that's the sliding in the sliding filament. You can see it here, right? See how there's some space, this little yellow beige colored space here, and then there's like a little gap here. Well, that space is less on both sides, and then there's a less of a gap here. This is a lengthened muscle, and this is a contracted muscle, right? This is longer than this. And that's what's happening in the sliding filament model. Whenever you make a muscular contraction, those two areas are going to kind of come together. And that's all doing that thanks to a bunch of this really interesting chemicals here. Eugenia, don't worry about what I'm about to say. I'm going to go through this very, very, very technical part. This actually isn't part of this class, but I want to review it for these guys because they've actually already heard this before. So I want to go through it with them really quick. This is going to sound like Latin. This is going to be pretty technical. But don't let it scare you too much. So what's going to happen is a nerve impulse, remember we call that an action potential, is going to be transmitted from neuron to neuron to neuron to neuron until eventually it synapses with a muscle fiber, right? And so, neuron to neuron until eventually that neuron grabs a muscle fiber. And that's what we call the neuromuscular junction, right? It's the area where those two are kind of meeting, right? It's a little gap like this. And then it's going to use acetylcholine, this little chemical, to run across that gap and bind to the muscle fiber, okay? Acetylcholine will bind to its fiber, and then that triggers an action potential, triggers an electric signal to run across the muscle fiber itself. Now, your muscle fiber has all of this stored calcium inside of it. And that calcium is then, once that electricity runs across, that's going to release all of that calcium into the muscle fiber, okay? So once that calcium is in there, those regulatory proteins, remember those are troponin and tropomyosin, they are attracted to calcium. So what they're going to do is they're going to move away to get to all of that calcium that got flushed in the area. Now, because it moved away, those binding sites on the actin are exposed. So myosin is going to reach up, grab the actin, and pull it. And that's going to happen in all of those myofilaments simultaneously. And so the ones over here are going to pull this way, the ones over here are going to pull this way, and the muscle cell is going to shorten. Once that impulse is over, your calcium concentration is going to get flushed out. The whole area is going to relax. Those proteins are going to go back into place, and your muscle cell is going to go back to its original resting length. And that is muscle contractions in a nutshell. How's everybody feeling about that? Checking in with all four of y'all. Pretty good, guys?
Yeah.
Awesome. Great. Awesome. Like I said, Eugenia, these guys, we're going to go over this every 6 weeks. So, and I'm going to spend a little time with you after this call as well, just to get you caught up and stuff. So if I move too quickly, don't worry. You're going to be an expert in no time. Okay, so let's zoom out. Let's let's stop talking about cells, right? Let's zoom all the way out and let's talk about how our muscles actually work, right? Well, before we look at how they work, we need to talk about sort of what they look like. So you've got different types of muscles, right? I always joke around and talk about how like I'm a pretty skinny guy. I tend to be a runner. So I've got a lot of like type 1 muscle fibers, but it's not like I don't have any type 2 muscle fibers. It's just I tend to be sort of a long, lean guy instead of a big, bulky guy, right? So when we look at our muscle fiber types, right, muscles are going to have different characteristics, and when we look at them, right, and that's how you're going to see, like when you look at these two guys right here, let's look at a marathoner versus a sprinter. Look at these two very similar but very different athletes, right? Like you can see here, very, very long, very, very lean, but here, very, very muscular, right? Well, this guy here is performing an event that lasts several hours. This guy here is performing an event that lasts a few seconds, right? Both are great events, and we love both of them equally, but they are very, very, very different. They're different types of muscle fibers because those different muscle fibers have different characteristics, so they perform different ways. If you were to ask this guy to run as fast as a sprinter, he's not going to be able to do it. But if you were to ask this guy to run as long as a marathoner, likewise, he's not going to be able to do it. So, different body types, right? So those different types of muscle fibers are going to be arranged all throughout your body. This is why, like your calves, for instance, like you need to do like a lot of calf work, high number of repetitions. They tend to be very type 1 muscle fibers. So because they're very type 1, you need to do a higher number of repetitions. Your arms are kind of the same way. Usually you have to do a higher number of reps in your arms when compared with like your legs or your big vanity muscles like your chest and back and stuff. So, you've got a combination of type 1 fibers and type 2 fibers running throughout your body. But labeling them out, what we see our type 1 fibers. These are what we refer to as slow twitch fibers. They're slow twitch fibers because they're smaller in size. They aren't as good at producing quite as much force. Generally, we associate type 1 fibers with things like stabilization or things like endurance, right? So your core, for instance, it's keeping me upright in my stool right now. That's an endurance activity, right? So those are type 1 fibers. They also have a lot of oxygen delivery, and they have lots of little what are called mitochondria, right? That is what allows those type 1 fibers to have so much endurance. They're able to continue producing energy on the go continuously because they get so much oxygen and nutrient delivery. And that means they're very slow to fatigue, right? Those are your type 1 fibers. They're your endurance fibers. They're a little smaller, they're a little thinner. But then you have type 2 fibers, and type 2 fibers are what we call fast twitch muscle fibers. These are much larger in size. These are much better at producing like a lot of force. And generally we associate our type 2 fibers with like maximum strength and like powerful contractions. When you think of lifting like a super heavy weight up over your head, or, a super heavy weight when you're squatting or lifting or whatever, those are very much type 2 muscle fibers, right? The problem with type 2 fibers is they're pretty quick to fatigue. You're really only going to get maybe 12 to 15 repetitions out of those at the most, but generally, you're getting like 1 to 10, and so those are very much like you're quick to fatigue, but they're much, much larger in size. So again, you've got a very type 1 style muscle body over here versus a very type 2 muscular body over here. Different things. And then type 2 is going to be split into further categories. You're going to see type 2A and you're going to have type 2X for extreme. Type 2X is the true fast twitch. This is like if you're doing up to 5 repetitions, you're just lifting so heavy that you get done with your 5th one and you need to take a nap afterwards, right? Because it's that hard. That's a type 2X style muscle fiber. But if you think about doing like maybe 12 repetitions or 8 repetitions, you know, where it's like relatively heavy, but it's still not like that much time, you know, it's relatively short in duration, that's your type 2A fibers. Usually type 2A fibers are actually what we look for in like professional athletes who are playing, you know, like NFL or baseball, you know, like we're looking, or like even like the NBA, which is still very much an endurance thing. A lot of times we are looking for type 2A fibers. You know, we want them to be really powerful, but we also want them to have some endurance, right? Rather than just being like extremely powerful with no endurance, or being extremely enduring, but having no power. Generally, type 2A is what you're looking for in most athletic sports. And that's around 6 to 12 repetitions most of the time. So we've also got a couple different muscle fiber arrangements here. You're not going to really ever be tested on these, but we'll talk about them for just a second here. You've got what are called fusiform muscles. Good examples of this are like your biceps. These are ones that are like parallel to your tendon. So they run in like the same direction. It's basically just like, you know, if you got a tendon here and a tendon here, you got a muscle running throughout, that's a fusiform. You've also got fan-shaped muscles like your pec. It kind of looks like a, you know, like a fan. So like that's here. Longitudinal, which are like actually parallel to your line of pull. So, you know, if I'm pulling in this direction, they're going to run in that same direction. Or you have quadrilateral, which are actually parallel to the line of pull. So your rhomboids, right? They're an example of that because they pull this way versus your sartorius, which kind of pulls this way. Unipeniform, right? That's going to be oblique, right? That's going to be on the outside. That usually causes like it's on the outside of a line of pull, so that usually causes rotational movements like this. Bipeniform, which is you know, your classic, this is exactly what you're thinking of when you think of like a muscle, right? So like just running from end to end and pulling, your quads are an example of that. And then multipeniform are the weird ones. These are the ones that have like multiple attachment sites, and they pull in different directions depending on what they're doing. Your shoulders are a good example of this, right? I can go this way and that way, and I can go that way, right? So I can do kind of all those things. Again, don't worry too much about knowing those guys. I usually just move right past that part. They don't test you on that at all, but it is kind of cool. I mean, you look at like how your muscles are shaped and how they're lined up. It, you know, you want to kind of draw a line from like where you see them start and where you see them end, and that will kind of tell you how they're going to shorten. You know, if you draw a line from here to here, that's how my bicep shortens. You know, you really draw a line from here to here, that's how my tricep, you know, shortens. Okay, so now we got to look at how our muscles are arranged throughout the body. So here's the thing about muscles, and this is your fun fact. If you remember one thing about muscles, I would say remember this. Muscles can only pull. You have no muscle in your body that can push. And I know that sounds surprising because obviously there is an exercise called a push-up. But muscles pull and then they relax, but they cannot push. So my bicep, for instance, can pull this way. It cannot push this way. So if I want to get my elbow back to like being nice and long, I need my opposite muscle on the other side to pull, right? I need to pull in both directions. And that is how our body moves, right? We have one muscle on one side of a joint. We always have an opposite muscle on the opposite side of the joint. So you're always going to have one muscle on one side and another muscle on the other side. Your muscles are arranged kind of like this. So when you look at it, right, you'll have a muscle over here. That's my best drawing of a muscle. And you'll have another muscle over here, and you'll have a bone running in between. That's a really weirdly shaped bone. It's the best I can do on both sides. And so this one, you know, this is going to pull this way, which will, you know, move the bone like that. This one's going to pull this way, which will move the bone like that. And so that's what we're going to see when we see this arrangement. Let's pull up a much better picture. Muscle. when you see like this opposite arrangement here, the classic example that we always look at is like your biceps versus your triceps, right? So you can see the tricep is contracting. It's right here. Now the arm is nice and straight, and this is pulled really thin. Versus when the bicep contracts, this is really kind of bulged out, and this is really thin, right? And so that's bulging and relaxing for the bicep, and then the opposite is happening in the tricep. That's happening throughout your entire body, right? So when you look at like an overactive versus an underactive muscle, ideally what we want to see is we want to see our muscles really balanced like this. But a lot of times, sort of the main thing we're talking about in this overall course is we're looking at how muscles are often overactive on one side of a joint and underactive on the other side of the joint. So you have like a muscle that's pulling too much on one side and not enough on the other. And so that causes this weird sort of funky angle here, right? So if my bicep was stuck like this, because maybe I only ever do like bicep curls and I never do anything for my triceps, I just all day, this is the only thing I ever do, right? What's going to happen is my elbows are eventually going to get stuck kind of like this. I'm going to walk around with this kind of weird, kind of bend here. I'm probably going to, sometimes you'll see it gives people like a weird lean forward. And so they'll have this kind of passive elbow bend instead of like allowing their arms to kind of hang straight at their sides all day. So they end up in this weird kind of bent position here. And that's not really what we want to see, right? That's what we see in an overactive muscle. And so we need to be able to identify those overactive muscles. And that's what we're going to do in the rest of this course, right? We're looking at how to identify those overactive muscles. But in order to do that, we need to understand like, how the muscles are arranged. And so when we look at it, we do have names for when a muscle is the main muscle, or when a muscle is a helper muscle, or when a muscle is the opposite muscle, right? So you have your muscles arranged as movers here. So this term we refer to whenever the muscle is the main muscle for like what we're talking about, we call that an agonist, right? An agonist is the main muscle acting as a prime mover. So for instance, like we're using the gluteus maximus as an example here, that's your butt, right? So your glute is the prime mover for hip extension. So if I want to move my hip this way, right? I want to take this bone right here and I want to move it in this direction. The main muscle that does that is my gluteus maximus, right? So this is the agonist for hip extension. This is hip extension. This is hip flexion, right? So this is the opposite of this, right? Or I should say this. I say no in my room. This is the opposite of this, right? So that's hip flexion, hip extension, right? So main muscle here, that's my main prime mover when I'm talking about hip extension. Well, the opposite muscle, the antagonist, right? So that's my agonist, that's the prime mover. My antagonist is my hip flexor, right? So my hip flexor complex does this. So I would say when I'm talking about hip extension, I would say my gluteus maximus is the agonist, and I would say my hip flexors are the antagonists because they do the exact opposite. Now I've also got synergist muscles. Synergist muscles are there to help. They are there to assist your prime movers. So down here at my hamstring, it's doing a little bit of extra work. It's helping my glute kick that leg back. So my hamstring complex back here is a synergist to my gluteus maximus. It is assisting in hip extension, right? So I've got a contraction happening here. This is the main muscle. This is a helper muscle. And then I've also got stabilizers, which are, in my hip and my core and bottom of my foot. That's all there to kind of keep my body in alignment while I'm doing these movements. So if I was talking about hip extension, the gluteus maximus is the prime mover. The hip flexor complex is the antagonist. And the hamstrings are a synergist. They're there to help. Meanwhile, my core, my rotator cuff, transverse abdominis, all of those muscles, they're there to stabilize. Let's use a different example. Let's say I was doing like a push-up, right? Like I'm doing, push-ups here. If I'm doing that, my prime mover is my pectoralis major, right? My synergists are my deltoid and my triceps. They're there to help, right? And my antagonist are things like my rhomboids, a little bit of my lats, and my middle trapezius, my upper back, right? Now, we don't usually actually refer to exercises when we're talking about these concepts. Usually we're talking about joint actions, right? So I've got like, knee extension. We've got knee extension versus knee flexion, right? So during knee extension, my prime mover are my quadriceps. My antagonist is my hamstrings. And my synergists are things like my adductors and abductors. Does that all make sense, guys? Pretty clear on those? Feeling good? All right. Now we've also got our endocrine system here, and you'll notice I didn't put any notes. I didn't put anything in your notes for the endocrine system because you're not going to be tested on it in this course. You'll get a couple questions related to it, but we'll go over it more in depth in other classes. So we're not going to spend a ton of time on that today. So your endocrine system, moving out of muscles here, this is your hormonal system, right? This is a series of glands and hormones running throughout your body. It's in charge of like controlling your body and creating certain physiologic processes, right? So you've got host organs, which will have these little glands that often sit on top of them. And then those glands will be released into your bloodstream in order to trigger certain physiologic events. So for example, you can see at the bottom of your brain here, you're going to have what's called your pituitary gland. This is sometimes referred to as the master gland, and it often signals things like your thyroid to release other types of hormones. So this will release what's called thyroid stimulating hormone, and it stimulates your thyroid. And then your thyroid will maybe sometimes release hormones throughout the rest of your body to trigger other stuff. So for instance, like growth hormone, that's what causes us to grow. Or, maybe this will actually travel all the way down to like your testes, your ovaries to generate like testosterone or estrogen or progesterone, right? You get your kidneys, which don't actually produce hormones, but they do act as a host for your adrenal glands. So your adrenal glands are actually going to sit on top of your kidneys there, and they're going to release adrenaline into your body when you need to get all amped up for exercise. So we've got a lot of different glands running throughout the body that are releasing a lot of different types of hormones, right? Like I said, the pituitary gland is the master gland. It's got these 3 individual little lobes that release different hormones. So for instance, it releases growth hormone, prolactin, oh God, so hard to say, adrenocorticotropic hormone. Actually, I did it. That's a hard one to say. Thyroid stimulating hormone, follicle stimulating hormone, that's a classic one. I don't produce enough of that. Luteinizing hormone, all these like little tiny hormones here that are, triggering other hormones to release certain other hormones, right? So that's what's kind of weird here is it's almost like a hormone hotline, like, thyroid stimulating hormone or FSH, right? This will really get released and then it will travel down to your testes, your ovaries, and that will trigger the release of estrogen or testosterone. So it's like, you need this gland to produce this hormone to make the other hormone make a hormone. It's a very sort of back and forth thing. You've got hormones running throughout your skin. You've got adrenal hormone for fluid retention. You've also got like oxytocin. This is my favorite hormone, by the way, oxytocin. This is sometimes referred to as the cuddle hormone or the hug hormone because your body will make it when you experience things like love and emotions that are really positive. Particularly like hugging can actually increase your oxytocin levels, which is kind of cool. And they actually, it is also the hormone responsible for triggering childbirth, which is why like sometimes that's actually what they'll say when when a woman's like expecting and she's like trying to go into labor. A lot of times what they'll do is they'll tell them, it's like, well, go home and talk about how much you love each other. It's weird. You'll talk about like how much you love each other and make that person feel very loved. It can trigger childbirth, which is kind of funny. But that's because your body starts producing oxytocin. And we all produce oxytocin, by the way, guys, girls, everybody. It's just that's one of its functions. So that's my favorite hormone. I think that one's fun. Like I said, you get thyroid. Thyroid is either going to speed up or slow down your body's cells. So that's why when you hear somebody says they have a fast metabolism, oftentimes they have a very active thyroid. You've got adrenal glands that's making your things like epinephrine and norepinephrine. That's actual adrenaline, triggering your fight or flight response. You've experienced this if you've ever been driving and someone like swerved out of their lane and you thought you were going to get hit and you're like, ugh, you kind of tense up and then like you just stay tense. That's because all that adrenaline is still running through your body. And so all your metabolism is like, let's go, it's ready to fight. And then you've got, like I said, you've got your testes and adrenal glands. Men and women both produce testosterone and estrogen, but men are producing about 10 times as much testosterone than women do, which is why men tend to have larger muscle fibers, because testosterone is how we trigger the production of type 2 muscle fibers. So we often see a lot of those much larger muscles in men due to those much higher testosterone levels. Also, you have got to control your blood sugar, and we use hormones to do that as well. This is probably the one hormone that we spend most of our time talking about, and this is going to be your insulin. So when you hear about somebody who has diabetes, right? So when you eat food, that food gets broken down into sugar, that sugar gets into your bloodstream. And then what it needs to do is it needs to get to your cells so that your, no problem, buddy. It needs to get to your cells so that you can produce energy in those cells, right? So we need that sugar in order to produce energy. So luckily, we like having, glucose in our blood, but your body also can't really use other materials in your blood if there's too much glucose in your blood. So what it will do is it will try to process that sugar out of your blood to get to normal levels if there's too much. So let's say you eat like a donut, right? Actually, you know what? Donuts are kind of fatty. Let's say you eat like a Thai iced tea. That's like the most sugary thing in the world, right? It's delicious, but it is full of sugar. So what's going to happen is your blood sugar is going to be crazy high. There's going to be all this sugar running throughout your blood, right? And so what's going to happen is your pancreas is going to produce this hormone called insulin. And insulin is going to get released into your bloodstream, and that will pull sugar out of your blood and convert it either into fat or it will convert it into glycogen. And that's why we often associate diabetes with obesity. This is somebody who has elevated their blood sugar levels so often that their insulin has converted so much of that sugar into fat, right? And that's why they say like sugar makes you fat. That's not a direct true translation, but there is certainly a correlation between the two. Now, obviously, what happens if you don't eat anything? Let's say you're fasting or something like that, or you just haven't had a chance to eat all day. Well, that's where your pancreas will produce this other hormone called glucagon. And glucagon is the exact opposite of insulin. If insulin's job is to pull sugar out of your blood and store it, glucagon's job is to release sugar from wherever it's stored back into your blood. And so like when you have a bunch of glycogen, which is stored in your liver and throughout in your muscles, glucagon will trigger the release of that sugar. And now your blood sugar levels, which might be really low, will get back to normal levels. But your body hates doing that. It wants to keep its stored glycogen as long as possible. So what it will do a lot of times is it will then also trigger other hormones that make you hungry. And then all of a sudden you're hungry and now you need to eat, and raise those blood sugar levels back up. So what's nice is we know that exercise can actually enhance our ability to use these hormones effectively. Like I said, you've also got epinephrine. Epinephrine is adrenaline a lot of times is what's more commonly referred to as. This is going to be in charge of like increasing your heart rate. Sometimes epinephrine can also trigger the release of glucagon, which will trigger the release of sugar. And it can open up your airways. This can actually trigger the opening of like the airways in your lungs. Epinephrine is often something that they will put in certain types of extreme inhaler situations. When somebody's having like an allergic reaction, for instance, they inject them with an EpiPen, which is epinephrine. And basically it's a precursor to adrenaline. Well, that causes their airways to open up and now they can suddenly breathe again. But now they also have all this adrenaline running through their body. So they're always, whenever you see somebody take an EpiPen, they're always like afterwards because it's triggering their fight or flight response. There's a really great, actually, I was about to say there's a really great movie. There's a really silly movie called Crank where this guy like injects himself with a bunch of EpiPens and he takes way too much. And then you just see him like, ah, and he just runs away. He's like super amped up. So again, hormones, they are going to be produced by both men and women. You have testosterone, estrogen. Both of those are produced by men and women. It's just that men make more testosterone, women make more estrogen. Cortisol, that's one that we all produce. That is a stress hormone. Cortisol also triggers the storage of fat. It also can trigger the breakdown of things like muscles. So we do not want to produce cortisol because that's how we lose muscle mass. Growth hormone, that's produced by both sexes as well. That's going to trigger cellular growth. Thyroid hormone, that's going to regulate your metabolism. But what's really cool is like exercise, because it is a stressful event, actually enhances the production of all of these hormones, and we really like hormones. So this is the laziest summary NASM's ever done. In summary, the muscular system is made up of all kinds of little individual muscle fibers. Those muscle fibers are going to slide and relax and slide and relax. And that's going to create that sort of muscular contraction there. And that is the PowerPoint, guys. How's everybody feeling? How do you guys feel today? Irene, Robert? Eugenia, how you feeling?
Good, thank you.
Yeah, you feeling confident?
Yeah.
So have you ever studied any of this stuff before?
No.
I'm very honest. I like right before, like when I was like calling, right before I like called you, I was like, this poor girl is coming into like, you're in the thick of it. Normally we don't start you this hard. This is a rough start. I love the emojis. But trust me, you're going to be an expert by the time I'm done with you. So Robert, if you want to, if you have any questions or anything, you can stick around and ask them. But if you got to bounce out of here, I'm going to spend a little bit of time with Eugenia here, and I'm going to end today's recording as well, and answer any of your questions kind of one-on-one. Robert, do you have any questions today though?
Yeah, we do have homework today though, right?
We do, yeah. We got homework 2 going out today. Or that's not true. We have homework 1 going out today because it's day 2.
Oh, okay. All right, for sure.
So yeah, just check Canvas. It'll be up in a little bit. The recording didn't get messed up today, so it'll be very much on time.
All right, for sure. You guys have a good day.
All right, you too, man. See ya.
See ya.
All right, really quick.